Okay, let's talk about something called implicit differentiation, and then we'll parlay that into using properties of logarithms to make differentiation a little bit easier. So first, a very brief introduction to implicit differentiation. It's a fancy way of saying the chain rule, because implicit differentiation really is just the chain rule, but it's done in a very weird way. I call it the chain rule on steroids. So I'm going to kind of expose you to implicit differentiation on a problem where it's not technically needed, but if I gave you the function y equals 5x cubed plus x squared plus 7x plus 1 and told you to find the derivative, you would just very quickly pop that out with your power rule. However, I'm going to chain rule each one of those, so I've rewritten the function y, except I've put parentheses around my x's, and I'm going to chain rule each one of these x's. So when I do this derivative, and this is going to be kind of the brains behind implicit differentiation. You chain rule everything. And so I'm going to bring my 3 down. 3 times 5 is 15. And the chain rule says you leave the inside alone. You don't touch the inside. And then you subtract 1 from the outside exponent. So here I brought down to 3. So 5x cubed differentiates to 15x squared. But then after you do the derivative, you then multiply. After you do the outside part, you then multiply by the derivative of the inside, and the derivative of x would be 1. Only this time I'm not going to write 1 for the derivative of x. I'm going to write it very weirdly, and I'm going to say that the derivative of x is, and I'm going to use Leibniz notation, it is the derivative of x with respect to x. Just like when I did the derivative of y over here, I wrote the derivative of y with respect to x as dy dx. The derivative of x with respect to x would be dx dx. And then we know that dx dx would end up being 1 because numerator and denominator are the same. They kind of cancel out. So I'm going to do the same thing with x squared. I'm going to bring down the 2. I'll leave the inside x alone and I'll subtract 1. But then I need to multiply by the derivative of the inside, which again would be a dx dx. Derivative of x with respect to x. Then I'm going to do the same thing with 7 times x. The derivative of 7 times x, well, if you put a 1 there, it'd be 7 times, and I'll leave the inside alone, to the 0 power, and then the derivative of the inside, the derivative of x, is going to be the derivative of x with respect to x is dx dx. And then when you look at all of those problems and you start simplifying, well, I've got 15 times x squared, and dx dx, because numerator and denominator are the same, that is the same thing as a 1, and so that's just a 1. So plus, move on, 2 times x to the first is just 2x, dx dx is 1, plus 7, anything to the 0 power is 1, and dx dx is again 1, so we end up with 15x squared plus 2x plus 7, which obviously I would not expect you to chain rule this one, but I wanted to show you that you could chain rule literally every single derivative you do in calculus, and that's how implicit differentiation is going to work. Now that example is kind of confusing because you're wondering why I did that, so let's look at some examples where you need to use implicit differentiation, and it's really used in problems where you cannot easily solve for y. So here I have 2 examples. The first one, you're thinking you could solve for y, you could subtract the x squared, but in the process of solving for y, you would have to create a square root symbol, which then you would have to say plus or minus, and you're actually creating 2 equations for the y. So in this case, I'm not going to solve for y. I'm going to look at this equation and I'm going to say, let's go ahead and just do the derivative of the entire equation. We're going to do the derivative of both sides of the equation with respect to x. And that's just like an algebra property. Whatever you do to one side, you have to do to the other, and that includes calculus operations. So when I differentiate the left side, I must differentiate the right side. So when I do the derivative, and the key thing is we are doing the derivative with respect to x. That means x is my primary variable. Your independent variable is the independent variable is the technical name for it. So the derivative of x squared with respect to x would just be 2x. But the problem comes with the y squared. So if I chain rule that y squared, the derivative of y squared would be 2 times y to the first, but then when I multiply by the derivative of the inside, this is a y, so I'm going to have to multiply by a dy dx, the same way I multiplied by a dx dx on this problem when the inside was an x. Well, here if you notice dy dx, now my top and bottom are no longer the same. Dy dx is not a 1, so we actually keep that in the problem. And then I go on to the right side of the equation, and the derivative of 9 is 0. So when I clean this up a little bit, I have 2x I have 2y to the first, which is just 2y, and then I have times dy dx is equal to 0. Then our challenge with implicit is we need to solve this equation for dy dx. And well, we'll do that by subtracting the 2x. So 2y times dy dx is equal to negative 2x. And then I will divide by the 2y. I'm going to divide by 2y. And that ends up giving me dy dx is negative 2x over 2y. And when simplifying is easy, I will do that. That simplifies to just negative x over y, and there is your derivative. And in true implicit differentiation problems, you will have x's and y's on both sides of the equation, or inside the derivative, I should say. So let's move on to number 3, the derivative of 5x cubed. Well, that's an x, so I don't have to do anything funky with that. By the way, I am differentiating this whole equation. Okay, sorry, I was just interrupted real quick there. I lost my train of thought. So we are differentiating this whole equation, so going from left to right, and remembering that we are doing the derivative with respect to x. Well, if I'm doing the derivative with respect to x, then any x term you just do your normal derivative. The derivative of 5x cubed is 15x squared. Nothing fancy there. But my next term, 3y squared, now I'm doing the derivative of not an x. Anything that's not an x gets what I call the implicit treatment. And the implicit treatment is essentially, you do the derivative normally. The derivative of 3y squared is going to be 6y, just like the derivative of 3x squared is 6x. But because this is not a y, we then have to multiply, this is not an x, so we then have to multiply by a dy dx. And so you do your derivatives normally, but anytime you differentiate a y term, you must remember to multiply by a dy dx. Moving on, I'm going to do the derivative of 2y as if it were a normal function. The derivative of 2y would just be 2, but that was a y term, so I now need to multiply by a dy dx. Anytime you do the derivative of something that is not an x, you have to tack on that implicit treatment of dy dx. And then I move to the right side, the derivative of 6 would be 0, and then we again have a challenge of solving for dy dx, and this one's going to be more difficult than the first one because there are 2 of them. We'll do the easy part first. I'm going to move the 15x squared over. I am solving for dy dx, so I want to keep all of my terms with the dy dx on the left side, but if you notice on the left side I now have only these 2 terms, and each one has a dy dx in it. What we'll do is we'll actually factor the dy dx out of those 2 terms. So we would have dy dx times the quantity 6y plus 2 is equal to negative 15x squared. And then if you can get that factoring step out of the way, then we will obviously divide by the 6y plus 2, and we end up with a derivative of negative 15x squared over 6y plus 2. And there is dy dx. And again, because there were y's all over the place in the original equation, we had to use implicit, and so my derivative has y's in the derivative equation, and that's okay with implicit differentiation. Okay, so why am I showing you implicit differentiation? I said I was going to talk about logs. Well, you can, I'm going to go back into logs here, you can actually use properties of logs that you learned in pre-cal algebra 2 to make your derivatives easier. And so I'm going to do that with number 4 here. As it's written, you could dive straight into the calculus and just do a chain rule. I could bring the 8 down, leave the inside alone to the 7th, and then multiply by the quotient rule. That's kind of an ugly derivative, and logs give you another option that I think makes the calculus easier. However, you do have to use a little bit of tougher algebra type concepts at the beginning. And so for this problem, I noticed that I have a fraction and I have an exponent, and there are properties of logs designed to deal with those 2 types of operations. And so I'm going to take advantage of that. I'm going to start by taking the natural log of both sides of this equation. So I'm going to say, actually I'm going to copy this. So what I'm going to do is I'm going to introduce a natural log to this equation, which I know that you're probably scared of that because y'all hate natural logs. But in doing that, I now have the option on the right side to use all of these properties. And I can start by pulling this 8 down and making it 8 times the natural log of this quotient. But then, now that I've gotten rid of that exponent, I can rewrite that log of the quotient into the log of the top minus the log of the bottom. And then all of that is times 8. So I use these properties of logs, and now instead of having this weird chain rule with a quotient inside it, I have just fairly simple logarithmic derivatives. And logs, in the world of derivatives, logs are not too bad. Now what you have to remember is that in order to do that, I uglified the left side of the equation. It went from a y to a natural log of y. And so now when we do the differentiation step, I've actually turned this into a slight implicit differentiation problem because I have to differentiate both sides. I have to do the derivative of ln(y) and the derivative of this right side. So the derivative of ln(y), well, let's think about if it were natural log x, the derivative of natural log x would just be 1 over x. So the derivative of natural log y is 1 over y. But that's not an x. So I did the derivative of something with a y, so I have to then multiply by dy dx. On the right side, the 8 I'm going to ignore. It's a constant times a bunch of stuff. And then these two derivatives should be easy. Logs are not too bad in the world of differentiation. So the derivative of natural log of x squared minus 2x, the argument, x squared minus 2x goes on bottom, and the derivative of that goes on top. So the derivative of x squared minus 2x is 2x minus 2. Minus the derivative of natural log of this stuff goes on bottom, x to the 5th minus 9, and the derivative of that, that's a jacked up 9. There we go. The derivative of that goes on top, right? And then because it's implicit, I have to solve for the dy dx. So my next step is going to be to multiply by a y. I'm going to multiply by y on both sides of the equation because that will get the dy dx by itself. And now I have a derivative dy dx of 8 times all of this stuff. But in this very last step, I'm not going to write times y. I just wrote it, but I'm going to erase it. I'm not going to write times y, and the reason I won't is because up here at the very beginning, I noticed that my function is only a function of x, like it's y equals, and there are only x's in that equation on the right side. So when I find the derivative, I should have only x's on the right side. This y is a slight problem, and we're going to fix that pretty easily because we know at the very beginning that y is equal to all of this stuff. And if that's what y is equal to, then I can actually plug all of that in the place of y right here. And instead of saying times y at the end, we will say times the original equation, which was that x squared minus 2x over x to the 5th plus 9 minus 9 all to the 8th. And so, so there is a way that logs can make the calculus easier. And I know that's a lot of work, but the calculus was easier. I didn't have to do a quotient rule or a chain rule with all this ugly stuff. The actual differentiation step was fairly straightforward. There was just a little bit of tougher pre-cal, and that's the choice you have to make. If you want to do the tougher pre-cal to make the calculus easier, go for it. If you want to jump straight into the derivative, you can, but it can get ugly. Let's do one more example. And so here I have the square root of all of this stuff, and again I see a bunch of products. I have x e to the x over sine. I have a quotient, so I'm multiplying, I'm dividing, and I have a weird exponent of 1/2. So if I were to do this derivative straight as it's written, I would bring down the 1/2, subtract 1. Then I would have to multiply by the derivative of the inside, which that's going to be rough because it is a quotient rule with a product rule in the numerator. That's a lot of layers to a derivative, so I'm going to unlayer that by introducing a natural log to the problem. And when I bring a natural log into the problem, I now can break apart all of this stuff. So I'm going to have the natural log of y is equal to, I'm going to start by bringing down that 1/2, natural log of x e to the x over sine x. But then in that natural log on the right side, I see a product in the numerator, and then I'm dividing by sine x, so I can split all of that up into the natural log of x minus the natural log of e to the x I'm sorry, that's plus. Those are both in the numerator. Then minus the natural log of sine x, and in that step, I now have gotten rid of all of that quotient product garbage. The left side is the natural log of y, which we now will have to implicitly differentiate, and we will do the derivative of both sides of this equation. Okay, the derivative of the natural log of y would be 1 over y, just like the derivative of natural log x is 1 over x, but that was not an x, so I have to multiply by dy dx. On the right side, I have 1/2. I'm going to leave that alone, so 1/2 times the derivative of ln x is 1 over x. The derivative of ln of e to the x, we could do two different ways. We could look at it and say, well, the derivative of natural log of something, you put the something in the bottom, and the derivative of that in the top. The derivative of e to the x is e to the x, and e to the x divided by e to the x would be 1, which makes sense because you should know that the natural log of e to the x does equal just x, and the derivative of x would be 1. And so if you applied the log derivative rule, you end up with 1. Over here, the natural log of sine x, the sine x goes on the bottom, the derivative of sine x goes on top, so that'll be a cosine x. And then to finish solving this, we will multiply both sides by a y. I'm going to multiply by a y. Over here, the y's cancel, and I end up with a final answer, and I'm going to clean this up just a little bit. When simplifying is convenient, I will simplify. So dy dx is 1/2 of 1 over x plus e to the x over e to the x is 1 minus cosine over sine is cotangent times y, but again, we know that y was equal to this stuff, so I'm going to take this stuff and plug it in the place of the y right here to give my final answer that looks like this. And so there is another example of how logarithms can make ugly derivatives a little bit nicer, but with the trade-off of a little bit more difficult pre-cal algebra 2 type properties of logs in the front end.